Okay, so I know I have an example of this type of stoichiometry in my notes, but I figured it might be nice for us to work through a problem together, just so you can get an idea of kind of the reasoning that you have to use to solve these types of problems. So last class, we talked all about molarity, and you had some simple molarity examples, just getting that idea of molarity of a solution equals the moles of the solute divided by the liters of the solution. So that gives us kind of a new conversion factor, a conversion factor between moles and liters. All right. So a lot of times we've been doing conversion factors, let's say like between grams and moles using our periodic table, or between moles and moles using our balanced equation. This is just another conversion factor that we can use when we're talking about the chemistry that's actually happening. Okay. The reason we do use molarity is because this is a little bit more realistic than kind of the problems we've been doing. You know, in lab, you probably remember that a lot of the chemicals we were mixing seemed like liquids. We said they were aqueous solutions. And really what we did is we dissolved some kind of solid crystal or salt in some kind of liquid, usually water. And so those had different molarities. So what we did is we broke up solid things into ions, so it made it easier for those ions to react. And then we measured a certain amount of that aqueous solution in some graduated cylinder and then mixed it with other things, and then we saw how the chemistry happened. So this problem here is actually a little bit more realistic than, let's say, mixing grams and grams, for example, okay, or mixing a certain grams of an aqueous solution, because we don't really measure volume of a liquid or an aqueous solution in grams. We would most likely measure that in milliliters, and then we'd have to know its concentration, or how many particles of stuff there is, moles of stuff there are per liter of solution. All right, so why don't you take a second. I'm going to have you grab your calculator. I'm going to have you grab your periodic table. I'm going to have you grab your ion chart. And the first thing, solubility chart. The first thing I'd like you to do is write this question down, pause the video, and then I want you to try and write a balanced equation for the reaction between silver fluoride and lithium carbonate. All right, so this is jumping back a couple of units ago, but something that's still good to practice. So write this question down, pause the video, and write a balanced chemical equation. Okay, so hopefully you have this balanced equation up here, Li2CO3 aqueous plus 2AgF, which is aqueous, produces Ag2CO3, which will be a solid. That's our silver carbonate. And then LiF, which is aqueous, and we've got a 2 out in front of that. Okay, so we're starting with a slightly different given than what we're used to. Normally we would be given, let's say, grams of silver fluoride, and I would say how many grams of silver carbonate can you produce. But in this case we're given a volume of our aqueous solution and its concentration. All right, and what we're still trying to find is grams of what we produce, because we are producing a solid, but we start with a different given. So there's a couple ways you can approach this problem. I like to do it kind of using the stoichiometry we've been doing, you know, writing out what we're given, canceling our units, and then getting our final answer. You can also use that molarity equation I gave you. If you like to do that first, that's totally fine. Okay, so what I'm going to start with is what's given to us. 36 milliliters of our 2.7 molar silver fluoride. So we'll start with our 36 milliliters of AgF, and then we're going to convert that to a different chemical. Now if you remember back before our quiz, when you're stuck or when you're trying to go from chemical to chemical, the best bet is to go to moles first, because these coefficients, remember, represent the mole to mole ratio. So right now we don't have moles of AgF, we've got milliliters of AgF. So what we're going to do is convert to moles of AgF. Right? This is one place that your chemical equation, molarity is moles per liter, can come into play, because you can take this and convert it to liters, and then use that relationship. Molarity is moles per liter. So we've got a molarity where we would have our liters, and we could solve for moles. I'm going to choose to do that using a fraction, which is still the same thing. It's still the same math, but to me this looks a little bit neater and is less writing. So first thing I want to do is turn these milliliters into liters. And there are 1,000 milliliters for every 1 liter, and we're still talking about AGF here. Right? And this would allow my units of milliliters to cancel. Right? And then to get to moles, I can use this relationship up here. Right? Because 2.7 molar silver fluoride is like saying there are 2.7 moles for every 1 liter of silver fluoride. Right? That's what molarity is. It's the relationship between moles and liters. So I can do another fraction here and say, hey, I know there are 2.7 moles of AGF for every 1 liter of AGF. And if you can see here, now my units, those cancel. All right? What we just did here, this is the only new part about molarity versus gram-to-gram calculations. Because at this point, if I did this math, I would have moles of AGF. All right? So what I want you to do is pause the video for a second. Now that you know you've got moles of AGF, I want you to take the next step and see if you can write what fraction should I put to, instead of having moles of AGF, get moles of Ag2CO3. So pause the video for a second and try and come up with that mole to mole ratio. Okay, hopefully you said, hey, mole to mole ratio, I know how to do that. That's just my balanced equation, right? And the way I relate moles of one chemical to moles of another is looking at the coefficients in front of our numbers. So based off my balanced equation, I know 2 moles of AGF are going to give me 1 mole of Ag2CO3. And when I do this, my moles of AGF are going to cancel. And at this point, we are almost done, because now we have moles of Ag2CO3. I'm not asking you for moles of Ag2CO3, though. I'm asking you for grams. So our last step is to go from moles to gram. That you should know how to do. So I'm going to have you pause the video again, take a second, maybe use some of your tools available to you, and go, okay, how can I get a relationship between grams and moles of Ag2CO3? Okay, so if you take a look at the screen, I'm hoping you said, hey, I can get a gram to mole relationship using molar mass. And we know that our molar mass is found on the periodic table. So you had 2 Ags, you had 1 C, you had 3 O's, and if you add up the molar mass of all of those, you should have gotten 275.74 grams. That's how many grams of silver carbonate there are for every 1 mole of silver carbonate. And if you look at my fraction here, my moles, those cancel. All right? So at this point, I've turned 36 milliliters of AGF into grams of Ag2CO3. The only last thing I have to do is do the actual math. So why don't you pause the video for a second and then see if you can come up with an answer. Okay, so again, a friendly reminder here. Anything that is on the bottom of fractions, we should be dividing by that. Anything that is on the top of fractions, we should be multiplying. All right? So we start with 36 milliliters of AGF. We're going to divide by 1,000. That's this step here. All right? Next step, we're going to multiply by 2.7. Our next step here, we're going to divide by 2. And our next step, we're going to multiply by 275.74. And when I do that, I've done all the math, right? So we end up with 13.4 grams of Ag2CO3. Then I just have to think about significant figures. I was given 2 numbers to start. So we've got 1, 2 significant figures and 1, 2 significant figures. So I think our answer should be rounded to 2 significant figures. That 4 rounds down. So we end up with just 13 grams of Ag2CO3, right? So again, I know this molarity stuff is a little new, but just think of it as another conversion factor, all right? Molarity is a way for us to relate moles of some substance to liters of substance, all right? And then the stoichiometry that we're doing is really similar to a gram to gram calculation. It's just now we've got that little step of using our molarity or our moles per liter to actually get a mole ratio, right? But again, if you start with a volume of some substance, you can use that molarity to say, okay, now I can do a moles of some substance and then a mole to mole ratio and then grams to moles, which is kind of what we've been doing earlier, right? So I hope this video helped. Thanks for tuning in.